Okay, hello everyone, and welcome to Handmade Hero, the show where we code a complete game live on Twitch. No engines, no libraries, no nothing. It's just us. And today we're starting a topic that's actually, unfortunately, bad news for everyone out there. Unfortunately, it's important. Yep. And I don't say unfortunately because of anything, like because it's bad to have important topics on Handmade Hero. Obviously, it's great to have important topics on Handmade Hero. I say unfortunately because really there is nothing inherently interesting, in some sense, you might say, when you try to solve problems given this thing that we're going to talk about today. It is literally just another layer you have to pile on to the problems that you already have. So it's not like optimization where you're talking about taking a problem and solving it down to a more fine level. This is not what this is. What we're talking about today is really, it just adds to your troubles. And in some sense, unfortunately, this is a thing that really programming languages and high-level stuff hasn't really solved that well either. It's just relatively nasty. And so on Handmade Hero, we'll try to show some ways that you can make it a lot less nasty and think about it as in sort of as simple a way as possible. But I won't lie to you, it is one of those things that has just been sort of creeping up on programming, and it keeps being more and more important to do, and it never really gets all that much easier. I'm beating around the bush, but of course the subject is multithreading. Multithreading is the process by which you have multiple simultaneously executing CPU cores or separate processors entirely working on problems together. And if you're lucky, you can separate them out so that the degree to which they have to communicate with each other is very small. If you're unlucky, then you cannot. And really that depends on the problem and sometimes your own ingenuity. Let's go to the blackboard first, and I'll talk a little bit about how this sort of stuff goes down, and then we'll sort of show how to create some threads and get them doing some things. I don't know how far we'll get into it today because we'll have to cover the basics in Win32 of how to actually make these things. But by tomorrow at least, we'll be at the point where we're actually having things happen, multi-threading. It's not that hard to get there. All right, so multi-threading. So first of all, let's just say very briefly what this even means and why this phrase exists the way it does. So you'll notice you have this thing called threading here, which we've never really talked about that much. And basically that's because there's these words that have been introduced in operating system parlance that have to do with certain degrees of execution granularity. And they tend to be process, thread, and fiber. What generally these things refer to are the degree of sort of logical separation that an operating system does between lines of execution. So let me just break them down for you very simply. So as you know, on Handmade Hero, right, we're writing a bunch of code. And that code looks like assembly language instructions. So there's like an ASM instruction, right, followed by another ASM instruction, followed by another ASM instruction, right? And there's a notion of where in the code we are. There's a thing called the instruction pointer we talked about, and it says, I'm here, and I'm going to do this instruction. I do this instruction, the instruction pointer moves down to the next one, I do the next one, right? And we also know there's a bunch of things like registers that are here. And we talked a little bit about things like translation look-aside buffer or the address table, and there's all these other things that the processor's doing that basically allow us to map memory and do all these sorts of things, right? So what I want you to think about here is just the fact that there's CPU state, right? There's all this CPU state that says a whole bunch of things that the CPU needs to know in order to execute an assembly language instruction. It needs to know which instruction it's executing, for starters. It needs to know what the memory layout is for the thing that it's using, right? Because we said everything's virtual memory, right? So it needs to know how addresses in the data map, or in the code, map to actual addresses on the physical chip of memory, memory chips. It needs to know what the register states are. Like we had these registers, right? We had those like SIMD wide registers. We were talking about moving things in and out of those registers. Well, it's got to have the registers, right? It's got to have all these sorts of things, right? Okay, so it's got that. The question is, how is this broken up, right? How is the operating system conceptualizing of this? Because we know that multiple processes, multiple like logical processes to us as users, multiple applications, I should say, are running at any given time. And as we talked about in Handmade Hero, each one of those has their own virtual address space, right? So Handmade Hero has a virtual address space that's its memory layout, but like Mischief has its own one, and they're both running on the same machine, okay? And so that is this granularity. That is what we call a process, okay? And what a process is essentially the state of the memory layout, right? The memory layout is controlled on the process level. And what that's basically saying is, okay, when you are running this particular application on the CPU, its memory layout looks like this, right? But the rest of this stuff is not per process, right? What ASM instructions are running, the translation look aside buffer and the addresses are part of memory, right? So this is all process stuff, right? Process. The registers, the assembly instructions, that stuff is not per process. It is actually done at a level below process, because each process may want to have multiple simultaneous, or not even simultaneous, possibly separate, code execution states, which is what we call threads. So underneath a process, inside a process, you actually have multiple threads. And threads are what store the rest of this stuff. A thread knows where it is in terms of what instructions it's executing. A thread has a state of the registers in the processor, right? And so what you have to start to think about is the fact that these are actually sort of like, there's like two levels, right? So there's processes which are sort of memory maps and a collection of threads. And then each individual thread stores additional state that has to do with the state of the processor beyond just what the memory map is, okay? So Handmade Hero is a process that runs, right? It's an executable. And inside that process, there are many threads that run. Right now, we have written one of those threads, the main execution thread. There are other threads that are running that the operating system starts that we have no control over. For example, direct sound starts some threads. The fact that we're using direct sound at all starts some threads in our process space that we have no control over, but that do things with the audio device. Well, the audio output, shouldn't say device. So there are multiple threads already in Handmade Hero, but only one of them have we actually written, okay? Now, in addition to processes and threads, there's also things called fibers, which we won't really talk about because they're not super necessary. But what a fiber is a thread and a fiber are very similar things. The difference is a thread is something that is actually a first-class operating system citizen that actually exists on the hardware, and the hardware actually can run multiple of them at the same time. A fiber is sort of a manual version of a thread. It's a thing that lets you save the CPU state for something, but they don't execute concurrently. You basically say, like, I'm capturing the state of this thing, and then I'm going to like restart it later or something like that. So we're not really going to talk about those because the reason that we're doing multi-threading is to take advantage of multiple CPU cores and stuff like this. We don't really need to worry about fibers. They were more things for overlapping work in the old days when you wanted to make it easier on yourself. And I really, all I can say about them is I don't really want to talk about them. They're not useful. But know that they did exist, and you know you can go look up more information about them if you care about them. But this is what we care about. All right. So why do we care about this at all, right? Why can't we just write everything in one thread? Well, the reason is because, as we've shown before, here in the Windows Task Manager, which I opened by hitting Control-Shift-Escape, which you can do as well, you can see the number of logical processing units that this CPU that I'm on has. Now, this is a Xeon machine. It was originally a very beefy machine. So as you can see, it has a ton of these. Your machine, if it's a modern machine, will probably only have 8 of these. I think mine has 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16. Never mind, it's got 16. So my processor setup has roughly twice the number of logical units as does the common modern desktop, which has 4 cores, each with 2 hyperthreads, or 8 slots, right? The reason I'm pointing this out is because each one of these things is capable of executing a thread simultaneously, effectively, right? So what that means is the fact that we've only written our code in Handmade Hero on a single thread means that no matter what we do, effectively there is, if there are 16 slots for executing things on the CPU, we have filled one of those slots, right? So we are effectively leaving, right, 15/16ths, if you will, of our performance potentially on the table, because the CPU can only actually fill one slot of execution with Handmade Hero, and the other 15 slots just sit around waiting. And maybe, if we're lucky, they do some work on behalf of the OS or something, right, like graphics driver or who knows what. But for the most part, because we only wrote one thread, the CPU can only execute one out of the 16 possible units can it even fill, right? So our goal with multi-threading on Handmade Hero, well, that's actually twofold, but the primary thing that we're talking about right now is we want to increase the number of threads that we have available to the processor to run so that it can fill up logical processing units with those threads and do more work on our behalf. Okay. So there's two types of sort of ways of thinking about this. There is a core and there is a hyperthread. And let's talk about what those are. We've mentioned them multiple times before, but just to be concrete. A core is a set of those units that we've talked about a bunch of times that can do work, right? So a core has instruction decoding, right? It has arithmetic logic units on it. It has memory units on it, right? And basically what a core is it's a set of units that can do work, like our multiplies, like looking up addresses. All of that stuff is what a core actually has on it, okay? Now a core, as we know, can issue several instructions per clock cycle if there are instructions available for it to issue. We just got done with 2 weeks of talking about stuff like that, right? So hopefully that's all fairly comfortable to you. You basically know, in fact, we were using that IACA thing to tell us about how many ports we could stuff with things and which instructions went on which ports, all those sorts of stuff, right? So the concept of a core, the core is that thing that we were looking at with the ports that could have stuff filled, right? But modern cores, the x64 cores that we're looking at here, like the one that's in this machine, the ones that's on your machine, at your for those of you watching at home, actually have the ability to issue instructions from more than one place at the same time. So a core that might have a bunch of units here, like we saw it have, like 5 ports or whatever, right? And each of those ports on any given cycle could accept something, right? So you could, if you had a port free and an instruction that could go into that port, you could issue it, right? And it could start doing work for you. Well, a hyperthread, right, is basically the same thing as a thread in terms of what it means, right? It's got this CPU state, it has a notion of where it is in an instruction stream, it has a notion of what the register state is. But unlike threads as they were defined before hyperthreading came along, what a hyperthread can do is actually run concurrently on the same core as another hyperthread at the same time. So in the past, you used to have one thread per logical core, right? So if I had a processor, right, and it had two cores, here's core A and here's core B, then what would happen is the operating system would assign one thread to each core. So this core would be running this thread, and this core would be running this thread. And that's the end of it. Here's thread A, here's thread B. They go on the cores. They operate simultaneously, but that's it. If one of these cores is actually a hyperthreading core, then what happens is it actually assigns more than one thread to the core. And it depends on the hyperthreading count. Some things handle 2 hyperthreads. This processor is 2 hyperthreads, I believe. Some hyperthreading cores can do like 4 hyperthreads. And basically, it's just how many slots the processor has for storing things like the registers and the instruction state and all that stuff, right? And what happens here is on any given clock cycle, right? So when the clock cycle, ticks over, and it's like it's time to execute like 4 instructions, right? I can execute, like we were saying, up to 4 instructions on a clock cycle. What it does is it looks at both threads and sees, do either of these two guys have instructions that can go into the ports that I have available, right? And so now, instead of the situation before, like like we were having, where it would look and it would go, oh, okay, here's all the instructions, here's these ASM instructions, right? Here's thread C, right? And here's these ADM instructions. Oh, they all go on port 1. All the instructions in the instruction window that I'm looking at go on port 1. So you know what? I can only execute I can only issue one instruction this clock cycle. I guess I'll have to waste the other 3 instructions that I could have issued if only they'd gone to different ports. Instead, what it will do is it will go, oh, well, you know what? I've also got thread B, right? And here's some ASM instructions there. And yeah, the first one goes on port 1, but the second one goes on port 0, and the third one goes on, on port 2, and the next one goes on port 0. I'm going to grab these other 2 as well, and now I can issue 3 instructions on this clock cycle instead of only having to issue 1. And so effectively, what you can think of this doing is it's as if it were sort of free for the core to switch which thread it was using at any time, and it can just bounce back between them all the time, even inside one clock cycle, right? Because it can literally just grab from either of the threads. So it's actually much more efficient than the old style where the operating system had to manually switch out these threads, right? Because instead of having to wait for the operating system to come in and switch out a thread, it can literally fill very tiny latency bubbles, on the order of a few cycles latency bubbles. It can fill those in by picking instructions from multiple streams, which if the 2 streams can sort of manage to like slot into each other nicely, where they, get into a phase where one guy's doing his memory while the other one's doing his computations and vice versa, this can be really symbiotic, and you can fill in a lot of the bubbles that way, right? So, okay. So let's talk about the thing I just said, which is I said something like the operating system comes in and switches, right? Because that's the next part we have to think about. So all right. So on a given core, and whether it's hyperthreading or not, there's typically more threads running at any given time than can fit on the cores, right? So we just said there are 16 slots on this processor, but the number of threads running in this machine is probably like in the hundreds, if not the thousands, right? And that's because, here you go. Here I open up processes. Look at all these processes. There are more processes running on this computer right now than there are execution slots, right? And each of these processes itself has threads, okay? So what that means is the operating system at any given time really has some giant set of threads, right? There's 1,000 of these or whatever, and it's only got 16 slots worth on this CPU, or like on your CPU, maybe 8 or whatever, worth of actual logical CPUs. These are often called logical CPUs. I keep using that term because like I said, or logical cores would be a better term for it. They're usually called logical cores because, again, they're not actual cores. A lot of times they're 2 hyperthreads, right, are both executing on one actual physical core. So there's always this concept between logical and physical cores. This machine probably has 8 physical cores, for example, but it has got 16 logical cores because each of the physical cores can have 2 threads on it, so it's as if there were more. Now, it's not as good as having a whole nother CPU core because it doesn't duplicate all those things like the ALU or the L1 cache or stuff like that. Those are shared. But it does allow you to run as many threads as if you actually had 16 actual cores. You just may not run them as fast as you could if you had 16 actual cores with all the duplicated stuff. But the hope is that you do run it somewhere near that fast, right? So if that was going to be twice as fast to run them on 16 physical cores, you're hoping maybe you get 1.4 or 1.3x. You get something, right? You're not going to get it all, but you'll get something. And maybe if you're really lucky, you get up close to it, 1.8, who knows? It depends on the workload, what's going to happen. But that's the goal, right? Because it's relatively cheap, my understanding anyway, is it's relatively cheap for Intel to add hyperthreads to a core as opposed to adding a whole nother core, because they don't have to duplicate things like the multiplier circuitry and the memory circuitry, whatever, that's the same. They just have to add things that allow multiple slots in terms of like the register file and stuff like that. Now, those things are still expensive. They're not free. So it's not like you can just have 100 hyperthreads and it's free, woohoo. It doesn't work that way because the routing and all that stuff is still expensive. I don't know very much about it, but that's why we don't have like tons of hyperthreads. But in order to get like a certain number of hyperthreads, it turns out to usually be a performance win. That's why they do it. It's cheaper to add hyperthreads than it would be to stamp out a whole new core. All right. So, and just to put a cherry on top of that, so you can imagine what they do at Intel is they basically look and go, okay, how underutilized is this are the set of things on a core typically, right? Like the ALU or whatever. How underutilized is that? And then they would want to add as many hyperthreads as would be necessary to utilize it. So, you know, if it takes 2 hyperthreads for typical workloads to fully utilize the actual work units of the core, then that's a good number of hyperthreads, right? If it takes 4 of them, then they would do that. If it takes 2 of them, they would do that. What you'll typically see, I believe, and this is again me sort of hand waving here because I'm not a hardware guy, so, you know, hardware guys feel free to correct me if I'm wrong. But what you'll typically see is out of order processors versus in order processors, right? The x64 is an out of order processor, which means it has that big window where it can grab instructions from, right? We talked about that a lot. What that means is that the degree to which it needs hyperthreading is drastically reduced because it's able to use stuff in the same thread a lot more efficiently than an in-order processor, which is a processor that has to execute the next instruction always, right? These stall a lot more on the same code because even if there were instructions, even if just the next instruction that you would have executed wouldn't have been blocked, the fact that the one you're on right now is blocked means you can't continue. And so these tend to benefit a lot more from more hyperthreads. So you might see, you know, 4 hyperthreads, right, on an in-order processor being common, whereas 2 hyperthreads on an out-of-order processor might be common. And that's because you don't need as many hyperthreads to give you the options that you need on an out-of-order processor, whereas on an in-order processor, you might need quite a few. 4 might not even be enough, right? So there you go. Okay, so here we go. I want to wrap this up so we can go show how to create some threads in Win32. Hopefully this gave you some idea about that, but what I want to talk about, one more thing today. We're going to save memory for tomorrow. One more thing today is the OS. So what's the OS doing? Well, honestly, these days I have no idea what the OS is doing. I have never seen a modern OS kernel, so I can't tell you. But it works something like this. There's a thing called an interrupt. All right. We haven't talked about these at all on Handmade Hero because you will never get to use them probably. The first time we'll probably ever get to use one of these for any real purpose is if we do Raspberry Pi programming or something like that where we're able to write sort of all the way down to the hardware and run as the kernel effectively. But on Windows, you probably will never deal with this. So, especially if you're just writing a game. So, what is an interrupt? Well, an interrupt is something where the processor itself decides to replace the thing that's currently running with something else, right? So basically what happens is you have that ASM code, right? And you've got an instruction pointer and it's going, right? So we're on some core, here's the core, we're running this stuff, and that's all fine and dandy. And then what happens is at some point you get an interrupt. And that interrupt might be like the scheduling timer, for example, in this case. So it might be an interrupt that just happens periodically, right? And what that interrupt does is it says, all right, hold on, I know you were gonna execute something. Don't execute that. Instead, I want you to execute this other code over here, right? And that code happens to be some operating system code. So when the operating system started up, back when you like booted Windows, right? It installed this interrupt. It installed a thing called an interrupt handler, which is this code. And it basically told the processor every so often, every millisecond or whatever, I want you to stop what you are doing. I want you to run my code, okay? And my code is going to do some stuff. Now, what this code will do is this code will see whether it wants to change which thread is running on this core. So, for example, what this code could do is it could issue a thing that says save the state of the processor, right? Save those registers, right? That register state. And the registers, by the way, includes this instruction pointer, right? Because that's actually a register in the processor. So save out all this stuff to a piece of memory somewhere, okay? Save it out. Load in somebody else's, right? Go grab some other state from some other thread and move it in here, and then resume what you were doing. Jump back in there, right? So effectively, what the OS does is it has a thing which every so often will interrupt what's running on a processor, possibly decide, it doesn't have to do this, but possibly decide that what should really be running on the processor is some other thread, possibly from some other process, in which case it'll also have the TLB, not the TLB, but it'll have the virtual addressing table. It'll pull in that memory mapping table as well. It'll swap that out, right? So it'll possibly do a whole bunch of work to change over the state, and then it will resume execution of some totally other thread, possibly from some totally other process, okay? So the operating system is the guy who's actually doing this work. It's doing it on an interrupt. That interrupt is allowing the operating system to come in and interrupt what someone's doing to let someone else do it. Now this is called preemption. And operating systems that work this way are called preemptive multitasking operating systems. Okay? A preemptive multitasking operating system is one that preempts the execution of a thread without that thread giving the operating system permission. Okay, this is how modern multitasking operating systems work. There are other styles called cooperative multitasking. Okay, and what those are ones where the operating system does not have this interrupt. Instead, what they have is every chain of execution, every thread, when it was written, has to have a thing in there that basically looks like yield. It basically says like, okay, I'm going to do a bunch of work and then I'm going to call yield. And yield actually physically calls out to the scheduler, right? So basically these are much more efficient, actually, because they never have these interrupts popping up ever. So that's kind of handy. But they are much less reliable for the user. Because what it means is that if one of these pieces of code is behaving badly or has a bug in it or just doesn't care, and it never calls yield, you can never switch what's running on that core, right? Once that launches, it's gone forever, right? So the reason that most modern operating systems are preemptive multitasking now is because it no longer requires the people who program these things to be good citizens, and it gets much more even load balancing because it can guarantee that it doesn't matter how this code was written, it can always preempt it at predefined intervals, right? Whereas with the cooperative one, it couldn't do that. So whereas this one can be made more efficient because you're never having these things happen at inopportune times, they can always be planned. They are much more reliable if they're preemptive because they can spread the work evenly, that's guaranteed, and they can make sure that bad actors don't suck up all the CPU time. Okay. So what do we have to do on Handmade Hero, right? Like I said, what we want to do right now, our goal for today, or our goal for this week, I should say, is we want to fill all 16 slots worth of cores, of logical cores on the processor. We want to fill those all with threads that the CPUs could be executing. And right now we only have one, right? So what we need to do is we need to give the operating system some threads it can start filling, right? It can start assigning to these processors, right? Because the operating system is the thing that assigns these, the operating system is the thing that schedules them, right? And so right now, basically what's happening is on all 16 slots, right? You know, we've got these 16 slots worth of processing that are happening, right? Most of them are just sitting there, right? Most of them are doing nothing. They're just waiting, right? And so the operating system is like running all of Handmade Hero basically on like one thread, and the rest of these guys are sitting around waiting. What we want to do is have it so that there's things in all the slots so the processor can kick them all off and get them all doing things. That's all we're trying to do here, right? And so when we look at this, graph, what you can see here is you can see that this number hovers around 11%, right? And we can see if we look at processes, you can see what's going on there. It's OBS that's taken that time, right? But we could probably get a little bit more explicit. Well, you know what we'll do? First of all, let's just run Handmade Hero. There we go. So if I run Handmade Hero, and we just have it running, right? I don't know if you can see that there. But, you know, this is going, you know, Handmade Heroes is going here. Here it goes. And right now, it's using like 3% of the CPU, right? And I guess that may actually be less than even a full single thread performance because there's just not enough rendering to do. So we may have to actually start making that, we may have to increase the render workload. But what I wanted to point out is we're hovering around 3% when we're doing our rendering right now of processor usage. And what we want to do is we want to be using like a tremendous amount, right? We want to be using basically 90% because that's what's left over from after OBS is running. We want to make sure that we're actually using all that. And so if we take a look at what that value actually means, right? 1/16 of a processor, right, is 6%, right? So right now we've optimized our render enough that with the current amount of work that we're asking it to do, we're not even using all of one core's worth, right? So the first thing we may have to do once we start doing our multi-threading is we may have to increase the graphics workload because we did a little bit too good of a job optimizing it. But that amount, that 1/16, that 0.06 there, 6%, if we did not increase the number of threads that Handmade Hero used for rendering, that would be the maximum amount of the CPU we'd ever see used by us. Because even if we fully max it out, so we add enough rendering work that it's in the renderer the whole time, right? And you know, it's working the entire time, does the blit to Windows and then goes right back to rendering, we would never see it get above 6% because without more cores going, we can't ever use more than 6% of the processor, right? So when you see this in the task manager and you wonder, why isn't my application running faster? it's only using 10% of the CPU and like it was dog slow or whatever, right? And I mean, we can even do this. In fact, I can do this pretty easily, and this would be maybe even a good way to illustrate it first off. If I go back and switch it to the super slow version, right, where we do draw rectangle quickly in our render group thing, where we were actually calling that, if I switched it back to calling draw rectangle slowly, right, then our game is super slow and crappy, right? You know, here we go, right? And here's our game. It's like barely functioning, right? So that's super slow. If we go look again at this is super slow frame rate, we can see that the CPU isn't pegged at all, right? And if we go back here and look at how much Handmade's taking advantage of, hey, look, it's the exact number that I calculated, 6%, right? And so again, the threading, what we're trying to do now is we're trying to say, okay, you know, modern processors, they count on this multi-threading a lot. And so we're never going to get all of the horsepower out of the processor if all we do is write the single-threaded code. We've got to push it into multi-threading in order to get above that amount. And if you think about how much processing is left on the table, if it actually worked out perfectly, and again, it never does, but if it actually worked out perfectly, right, using 60% of the processor would be 10 times faster, right? That's how much is left on the table there. And 60% ain't 100. There's even, you know, after 60%, there's like another 2 extra, right? So we're talking about something in the order of like 17% or something like this, 16x, because we know we're only filling one slot and we've got 16 processors. So we're talking about 16 times the performance we could get if we filled those out. Now, you won't get actually all 16 for, like I said, because, you know, some of those are logical cores, not actual cores, and then there's memory issues and all these other sorts of things, and handshaking, blah, 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 blah. So we probably won't get 16x, but, you know, 10x, totally plausible, right? And 10x is huge. So that's, again, why it's so important. And again, the reason why this is the case, you may wonder whose really bad idea it was to make these processors require this, because why do we have to care? Why can't we just write the code single-threaded? And why didn't they just make a processor that executes a single-threaded code is very fast? The answer is heat, unfortunately. So basically, like, heat is bad, is basically the problem. So what they found out, there was an architecture, it was called the Pentium 6 or the P6 or whatever. It was the thing after the Pentium, right? So there's the Pentium, and then they made the P6. And the P6 was designed to scale to very high clock rates. So they were like, oh yeah, you know, like we're gonna make this run 8 gigahertz or something, right? What they found is when they got up to 4 gigahertz, the chip melted, basically, right? And they just did not anticipate how much heat these things would generate and how much the heat would be a problem. And to my knowledge, to this day, they pretty much never solved this problem. Like, the heat just is flat out not solvable at the moment. I don't know chip design, so I can't speak to that. Again, that may be not quite true. But basically what happened is, right around this period, they hit a heat barrier, and the heat barrier has never been breached. It's basically just a hard limit. So you will never see the 8 gigahertz CPU. Well, someday you might, but you didn't see an 8 gigahertz CPU in the last decade, specifically because of this, otherwise you would have. And so what they quickly found was that they cannot increase the clock rate any more than they already have. And what that means is they've had to do other things. And what were those other things? Well, number one is wide execution, right? And we saw that. That's like, all right, if we can't go any faster, maybe we can go the same speed, but do the operation on 4 times as many things. And that was SIMD, right? That was 4 times as many things, 8 times as many things, 16 times as many things in AVX 512, right? And we already took advantage of that. That was the first set of optimizations we did, right? And we didn't really have to optimize much. Really, all we did was just make the routine wide, and hey, it got a ton faster, right? So that's what that is, and that's a way of getting 4x performance, 8x performance, 60% performance, right? through the CPU just by saying, okay, instructions, instead of operating on one thing, now operate on way more things, right? So that's a way to make the speed not change, but the work amount change. So that's the first thing they did. Number two was more execution, right? And that's what threads are. They were just like, all right, if we can't go any faster, let's just execute more different programs at once, right? And we'll just hope that the programmers can figure out ways of breaking their work up into multiple simultaneous programs. And so that's where we're at today. And that's why optimization today largely boils down to how well you can do these two things, because at the end of the day, this is where all of the processor horsepower now goes. It's getting wider and getting more execution at the same time, right? And so we've already looked at how to do this, and you kind of have an idea of how to write routines to do this now. And so this is the second thing that we're trying to do now. We've got about 15, 18 minutes left. And so what I want to do is pop back to Win32 and show you how to do the basics. Okay, so hopefully everyone's kind of clear on that. And there's not a lot of mystery there. It's at its core, again, it's a very simple concept. It's just saying, hey, before you could execute one thing, now you can have multiple things executing at the same time. But other than that, they're basically the same, right? And there's a bunch of nuance to it that we'll start going into over the next couple days, but that's really about it. And really it gets down to memory. The way you deal with memory and synchronization issues tends to be the part that's really hard about multi-threading. You'll already see there's already one thing we'll have to change in the way that we're filling our rectangles because of the way cache line boundaries work and stuff like this. So there's one thing we'll have to do there, and then there's another thing that we'll have to do in terms of letting people know which threads are supposed to do what. But that's basically like, you know, where the actual difficulty comes in. So here we are in Win32 Handmade, right? And what you can see here is, you know, when we wrote this code, we never really talked about threading at all. And the reason for that is because by default, things were set up the same way they were in the old days, right? Like Windows still launches your app exactly the way they used to be in the old days, which is to say that in the old days, there was only one thread of execution anyway. So you called into WinMain, and it was just a given that that was one thread, and this was the thread of execution. So everything pretty much happened on that thread, and here it is happening on that thread. So if we want more threads, and we want to start control more threads, we need a way of telling the operating system, hey, I need to start making more threads. Give me more execution context, please. And so as you might expect, the way to do that is with a function called createThread. It's actually fairly straightforward, as some things in Windows actually are. Oftentimes the things in the Windows kernel are actually pretty well thought out, because honestly, the guys who originally wrote the Windows kernel were pretty darn smart, and actually, unlike people who write a lot of the Windows API, they were very experienced as well, which makes a huge difference. And so some of the things that they do are really actually pretty well thought out. I'm not going to say that createThread is perfect or anything like that, but I'll just say that a lot of the Windows kernel stuff is done in a very nice way. I/O completion ports, for example. I/O completion ports, which we'll use a little later on, are probably one of the best APIs that exists in Windows. Actually, it's almost perfect. And that's not something that you pretty much ever say about a Windows API or anyone else's API for that matter. All right. So we have a function here that we're going to call, and I'll just call it right at the top for now. We'll worry about where we're going to call it a little bit later. I just want to show you how it works. We have a function here called createThread. Okay, and what that does is it returns us a handle to the thread. This is our thread. Oops. Our thread handle. Okay, and it takes a bunch of things in. First of all, it takes these LP security attributes, and what those are is we don't really care very much about those. I think we bumped into them once before, and we said we didn't care about them there. We also don't care about them here. What those are is these things that you can do if you wanted a thread that you were creating to not have the same permissions that you have, right? And so we don't really care about that, so we're just going to pass null, which basically says that, you know, the thread that I'm creating should be able to do anything that I can do. But you can imagine in other security scenarios where you wanted a thread to have restricted ability to call Win32 calls, like, oh, I don't know, I'm trying to protect against some kind of hack soaring, so I just don't want this thread to be able to call some stuff. I don't know, whatever. You can imagine maybe some cases where you want to do that. In games, you rarely have that case, but maybe a web browser or somebody else wants to do stuff like that. Okay. So then we've got the actual meat of the thing here. We've got the stack size, right? And you can see what this is. What we can do here is we can basically say we want to use whatever one we were using for all the other threads, right? Which is if we pass 0. So again, we can just pass essentially default values for these two, and nothing will change. That stack size is whatever we specified when we built the executable. So in the build.bat file, right, we didn't actually put one in here, but if later on we wanted to, we can control the stack size in here. We played around with that a little in early Handmade Hero. But so we're just going to use the default again, but we could change it. Then we get down to the meat of it, which is the start address and the LP parameter. And basically what these are is just saying, okay, what's the actual code for this thread? Like what's actually going to happen, right? And so what you do is you create one of these guys. It's this is what it looks like, right? You create one of these guys called a thread proc, and this is the actual parameter. I guess I can leave it like that. It doesn't actually matter in Win64, but that's a separate issue. This is actually what the code is going to be for this thread, right? It's the entry point for the thread. So just like WinMain was where we got started calling, although technically it was in the CRT that first got called, but point being, we basically have an entry point where this thread is going to start executing, and then it's going to do something in here, and then it's going to, when it's done, it'll exit out, and that'll be the end of the thread, right? So if we want to, we can do output debug string, thread started, or something like this, and that's fine. And this would be the code for the thread. That's all the thread would do. And what we do is we pass that address to create thread and say, that's where I want you to start executing, right? And then what we can do is we can also pass a parameter to the thread, and that parameter is what comes in right here, right? So whatever we pass as the next thing is the thing that comes in here. So right now, we don't actually have anything, but we have param equals 0. We'll just put it there and leave it there for right now. That's what, and then later we'll actually worry about what we're going to pass it. And that's what will come in here. In fact, we could do something like this just to show it. Thread started, like so. We could do it this way, where we just say string to print equals whatever this LP parameter was casted. Oops. And then we print it, right? Like so. And this way we're passing in that, right? So we call that, just like that, not really anything particularly too weird there. We then have two more things, which is the creation flags, and you can see those, again, always using MSDN. You can see those here. And basically what these are is special ways that we might want to do stuff. So normally, if we just pass a 0, which is what we're going to do here, the thread just starts executing right away, right? But if we'd wanted to, we could create it so that the thread gets created but doesn't actually start executing until we call an additional function. So if we want to create a bunch of threads that are just waiting, like horses at the start of a race, until the gates open and they are allowed to start running, basically like that resume thread would be the thing that actually starts them going, right? So if we wanted to, we can create the threads and not have them run yet. But we don't really care about that, so we're going to do that. This guy I don't even remember this guy being in here. But you can see here, this is basically a thing which says whether you want to do reserves or commits on the stack memory. I don't know. That must have been something that they needed to do at some point, so they had to flag for it. We're definitely not going to ever look at that. Okay, so then finally, and this is the part that's a little bit weird in Windows, threads are identified both by a handle and by an identifier. Okay? And I feel like this was kind of a mistake, but I don't know. Maybe they had a really good reason for it. I've never really grokked why they thought this was a good idea. But so they basically have a thread ID that identifies the thread, and it will give you that as a return value as well. So not only do you get back a handle, which you can use to operate on the thread, you also get back an ID, which you can also use to operate on the thread in different ways, right? So you basically have this thread ID here, and we pass the address of that thread ID dword, and it will fill it out. It's a return value, essentially. It will fill it out with the value. So if we actually do this, if we actually run this code, that's actually all we need to start multi-threaded for the most part. Oops, I got to actually return something here, right? This actually returns a dword. That's actually all we need to actually get multi-threading started. And if we actually run the code here, and I just run the code and then exit, or try to exit anyway. Stop. In theory, we should be able to see that work. Now, of course, I didn't actually see it here. I'm not sure why we didn't see it. Oh, yes, we did. There it is. It's up here. So you can see it right here, right? So here's the thread started call, and then you can see immediately after it that thread exited, right? And so literally this is just something that happened on a totally separate execution path than the rest of the code, and it just, that was it, right? And again, we'll be able to demonstrate this a little bit more explicitly a little bit later on, but you know, that is literally the entirety of how you get multi-threading started. And so you can create as many of these as you want, right? You can imagine us creating lots of these threads if that's what we wanted to do. We could do that like so. We can just keep on creating threads all day long, and no one's going to stop us, right? And so if we want to do that, we can do that. Off we go. That just creates a bunch of threads, all of which call that initial thing, and you can see them all happening here, right? And they happen in exit, right? So that's really about it. However, there's some additional work that we probably want to do here just to sort of solidify things a little bit, which is that when we call this create thread, we get back this thread handle, okay? And the thread handle, like I said, is something that allows us to do operations on that thread, right? So once we have a thread handle, like for example, we could destroy the thread, or we can, like that resume thread call that you saw, if you were to create the thread suspended, the resume thread call, you can see that basically what they do is they take that thread handle, and that's a way that you can refer to this particular thread, right? Now, when we don't want it anymore, if we don't want that handle anymore, we can call close handle, which basically says to Windows, we're not going to talk about this thread anymore, right? We're just not. It's not going to happen, right? And so we can actually do that. We can actually say we don't care about this anymore and say close handle, right? Thread handle. But what's important to remember is that doesn't kill the thread. The thread is still going. It just says, closing the handle says, you know what, I don't need to talk about this thread anymore. It's off doing its thing. I'm not going to explicitly manhandle it. And so you can just release that handle back to the operating system just by doing that, right? And what we can see here, if I add in something, like say I did something like this, oops, where I was just going to print this string out over and over and over and over again, ad infinitum, right? And maybe I introduce a sleep here so it doesn't spam it too much. So this thing is just going to, every second, it's going to print this out, right? What we can see here, if I do this, is, yeah, I know it's unreachable code. What do you want me to do? I got to return a value. Oh, is this one of those catch-22s? No, okay. So off we go. I run this code. And what you can see here is that even though I've closed that handle, the thread started message is still getting printed, right? And that's just going to keep on going. That thread's just going to keep on doing that thing because the close handle is just releasing the handle back to the operating system and saying, I don't need to talk about this thread anymore, right? But it's still going to be running. It's still going to be doing its execution path, right? So whether we want to or not, I don't know. Whether we need to talk about it later, we'll see. But for now, you can just see, okay, we created it. It's off. It's running. We're done, right? And that's about it. That's really the end of it. So what we would need to do here, right, is we would need to have some way for this thing to eventually exit, right? Because otherwise, whatever it's doing is still going to keep on going even after our game is like, our game is supposed to exit and this thread is still running, right? And so let's take a look at what happens there. Actually, I'll show you what I mean by that. So our game, I'm going to actually go stop that draw rectangle slowly from eating up all of our time. I'm going to put it back to the fast mode just so we're in a more well-functioning system. So here we go. Here's the game. And if I remember correctly, I believe Alt F4 closes our application, right? So when we do Alt F4, right, and it closes the application, I believe what happens is we do an exit process, right? Well, you know what? I don't actually remember what we did. So let's actually go take a look at what we did. Here we go, Win32 Handmade. So I don't actually remember what happens here, to be honest with you. I do not know. So let's take a look. Exit process. Do we call exit oops. exit process anywhere? We do not. So what happens in our WM close handler? Right? Because like we're doing Alt F4. Global running equals false. All right, let's take a look. Oh. So that code gets optimized out. Oh, this is an optimized build. All right. So never mind. I will go into the build and change it back. There we go. All right, because I want to see what happens when we do that. So we hit Alt F4. There we go. Global running equals false. And so now we should fall out of our loop up here, right? Because we've got this while global running situation here. Oops, that's not it. That's the simple one. Where is our actual while global running? Hello? There it is. That's the one. So when we get here, right, global running is now going to be false. So when we actually come through here, we're going to return 0, right? And if we actually step through, what happens here, we pop out, right? And this is in the C runtime library, right? And I imagine that's probably what's going to happen is it's going to call the exit process for us. I'm not actually sure. We'll find out. Let's take a look. Man, oh man. I assume we're going through trying to call C++ destructors here. Yeah, it's so much fun. Oh, the C++ of it all. Okay. Exit process. CR2 exit process. Get module handle. There it is. So what you can see here is eventually the C runtime library calls exit process for us, right? Here in their lovely C++ cleanup code that's going through and trying to call global destructors and God knows what else it's doing. Here is the exit process call, and that exit process call is actually what kills our other thread, right? Because that other thread is just going, right? And it would just keep on running, and our process would never exit because we have that thread running. But exit process basically terminates all the threads, right? So right here you can see the very first thing that happens. All of these threads just get terminated basically without any regard to where they were, okay? So that is what actually allows our application to exit. If exit process were not being called by the C runtime library, that thread would just keep on running. And so it's worth, the reason I bring that up is because, for example, one thing we have not done yet in Handmade Hero, but what we might do in the future is build without the C runtime library at all. In fact, we probably will do that sometime in the future when we're in the mood to do so. Because again, we like to do things from scratch here, so it'd be nice to get that out of there. It's worth noting, we would have to call exit process in order to actually kill this thread. Because once we get rid of the handle, and if we're not actually looking up by the thread ID or anything like that and trying to kill the thread, we would have to do that. Now there's another way we could do that, right? We could say that in there, in Win32 Handmade, we could actually make this guy also look at that, right? We could say that this guy also looks at while global running, and he will exit when global running is signaled as well, right? Because, again, threads share all the same memory. They're not separate processes, they're separate threads. So what that means is that any piece of information that we want to look at, we can actually look at, right? Now, there's a catch, and this gets into what we start talking about tomorrow probably, although maybe not, we might get into this, we might not get into this till Wednesday, is that the compiler doesn't, unfortunately, know about these sorts of things. It doesn't know about threading. So actually doing this may or may not work, right? It depends. And what it depends on is whether the compiler tries to reload this value or not, right? Because remember the optimizing compiler, how the optimizing compiler worked, where it would, you know, the optimizing compiler would basically say, oh, well, global running, maybe I know that that never changes, so I don't have to actually reload it from memory every time. It might do something like that, not realizing that some other thread, right, unbeknownst to us, is what's actually going to go change global running. So there's things like markup like volatile and stuff that we might need to use to make this sort of stuff work. Right? So for now, we'll leave that. I just wanted to point that out. And it's time to wrap up anyway, so we'll go ahead and go to the Q&A. That is a very brief introduction to threading. Tomorrow what we'll do is we'll create a bunch of these threads and figure out how to start pointing them at the renderer, if that makes sense. But hopefully that was a reasonable introduction to threading. And now I will take questions on that. Let's type Q&A. There we go. What does closing the handle of a thread do for you when you release the handle to the OS? Does it open up resources and increase performance? So in our case, nothing really. I mean, the way that we're going to do stuff is we're going to create 16 threads, basically, or 15 threads, and then we'll have the 16th from the one we have here, or whatever. And we don't really have to close those handles. It doesn't matter. But the reason I pointed it out was because it is creating a handle. So what it means is that there's only a certain number of handles and so on. So closing them might free up some slots for the operating system. It doesn't matter. Honestly, it really doesn't matter. I just wanted to point it out. It's sort of good housekeeping to say, okay, if I'm not going to use the handle anymore, I'll free it. But really, in the way we're using it, no. You could just go ahead and let the handle leak, and it wouldn't matter at all. So in practice, nothing. There's no difference. Doesn't increasing the number of threads to match the hyperthreads count increase cross-core, cross-context switches, thus making it less efficient for small operations? Well, it depends. So basically what you have to keep in mind is how much overhead are you introducing for your multiple threads, right? And that's something that we haven't really talked about yet, because we haven't started actually doing work on these threads. But there's a question of how much overhead are you introducing to have the secondary thread? If that overhead, in terms of like how it communicates and how the work has to be done differently to partition it, if that overhead is very small, then it's unlikely that you will then it's unlikely that you'll ever get a lose from using the same number of threads as there are hyperthread slots available in the machine. But if you are actually creating more work and more, like if you're creating a lot of extra stuff that happens there in terms of getting the hyperthreading, getting up to the number of threads that you need, then that can definitely be the case. It may be the case that you really only want to increase it to the number of actual cores, not to the number of hypercores. But again, the only real way you can know that is by testing it. So you probably want to, if you really care about the performance, try it at least first before deciding ahead of time that you think it's one way or the other, because you probably aren't going to guess right. Is there any advantage to creating a separate process to render the graphics in the context of game development? Probably not. The only reason you would want to create a separate process is if you were worried about security. But there isn't really much reason to create a separate process to render graphics otherwise, because I mean, okay, so there's one other reason. It would be if you were on 32-bit Windows instead of 64-bit Windows, which is becoming increasingly rare, so I doubt that anyone would do this anymore. But if you were on 32-bit Windows, you would get more memory. Because remember, each process has its own virtual memory space, which on 32-bit Windows is 2 gigabytes of memory for the process memory, and 2 gigabytes of memory for kernel mapped memory and other things, right? So if you needed more than a 2 gig split, and you wanted your game to, say, have a 4 gig split, if you broke the game into 2 processes, each process gets its own 2 gigabytes, right? So, I mean, in some real crazy scenario, maybe. But on 64-bit Windows, I don't think there's really any reason you would want to do it if it wasn't for making a security partition, because in 64-bit Windows you have way more memory addressing space than you could possibly need, and so there wouldn't be any reason to go breaking it up into multiple processes like that. Is it still a while yet before we look at other platform layers other than Win32? Yeah, so just to be clear on that, I've said it a couple times, I'll say it again. We won't be doing multiple platform layers until we're ready to ship, because otherwise we're just wasting work, because we want one platform layer that has all the stuff in it that we know we need. So we want the game to basically be done and having all the platform support that we know that we need, and then we just port just that, instead of trying to maintain multiple platform layers at a time, which just wastes a lot of work, right? Why just 15 threads? Why not future-proof? So when I say 16 threads, I'm talking about on this particular machine. What we will be doing is not creating 16 magical threads and saying that's good, because that would actually be too many threads for people who have only a 4-core 2 hyperthread processor, right? So what we will actually be doing is we'll be calling a function that asks the operating system how many processors there actually are, and that's how many threads we'll be creating. Will we be querying the system for its CPU count to determine how many threads to use? Yes. And we will also try to, and in fact this is the next question, do you have control over on which core the thread executes from the program itself? And the answer is to some degree yes. And so what we will be doing is we'll be using operating system calls to basically say, how many processors are there? To what extent can you tell me, Mr. Operating System, which of these logical processors share resources, like caches, right? And that's the hyperthread thing, right? Because 2 hyperthreads share resources on a core. And then we will be using that information to, as best as we can, create the right number of threads and hint to the operating system which cores we want those threads to run on, so that we will try to make it so that if the thing has, 8 cores with 2 hyperthreads each, we actually create 2 threads per core to run and know which 2 they are, so that they can work on the correct workloads to try to maximize the cache usage. So we will try to do that. And Windows does give you calls that that allow you to do those sorts of things. Do you plan to make pathfinding multi-threaded? So I don't think we will probably multi-thread pathfinding specifically itself. What I suspect we will do is multi-thread simulation in general. And so that all of the simulation stuff can happen multi-threaded if we want it to. We'll see. I'm not sure, but we'll see. Jonathan Blow had created 10,000 threads on his compiler demo. Some people wondered how in the world that could happen. Well, a thread is just a CPU state. So you can create hundreds of thousands of them. You can create 1 million of them if you wanted to. It's only limited by the amount of storage space the operating system will allow you to use for storing thread state. That's it. Because remember, there's only 16 of them, like on this processor, that are happening on the processor. So the rest of it is just memory that the operating system is reserving to store the state of a thread that it might swap in at some point, right? That's it. So creating a thread is not a big deal, right? You wouldn't ever want to create 10,000 threads because you're just wasting a bunch of resources and slowing things down because the operating system has to swap them in. So typically you only want as many threads as can actually execute on the processor, right? But you can create as many as you want up to the limit that the operating system, until the operating system just says I'm out of space, right? I think all the rest of the questions were not on topic. Do we have any other on topic questions first? Let me make sure. And by the way, Garlando Bloom is totally right. Obviously, no one will ever need more than 16 threads or 2 gigabytes of RAM. Clearly. And D7 Samurai is also correct that no one will ever need more than 256 colors. We just know these limits, they're so high. How could you ever use more than 256 colors? I don't even know. Like, how many colors can you name? Red, green, blue, cyan, magenta. I mean, that's it, right? I mean, you probably only need like 16 colors, really. Okay, I dare you, there aren't even 256 colors in one of those big boxes of Crayola. So clearly, these limits are totally fine. All right, so it doesn't look like there's any more on-topic questions, so I'll address a couple of the off-topic ones. Why I use C over C++? I would note we do use some C++ features occasionally. Operator overloading, function overloading, and declare anywhere are C++ features that we use. Now granted, declare anywhere I think now is in C99, so that's not really a C++ feature, I guess, but just point being. When I started using it, it was a C++ feature back in the 90s. But the reason that I don't use C++ is because almost all the features of C++ are bad. They're poorly implemented, they don't work very well, they end up wasting a lot of code and producing lousy output code. They're just really bad. C++ is a lousy language and most of its features are lousy, so I don't use them. C is a pretty good language and most of its features are good. I wish it had other features. There are a bunch of features I wish C had that it doesn't. Unfortunately, C++ doesn't add those features. It adds other lousy features, and you know, what are you gonna do? Can we stay on stream after I end the episode recording for another try on the story? Yes, I will stay on and we can try that again. 2 other questions. Which programmer's code you'd recommend reading? I don't know. I don't spend a lot of time reading other people's code, and I'm not sure what you mean by that. If you mean like to pick up good habits in coding or to learn about how to implement algorithms, like it would depend, right? And that stuff's pretty preference oriented. So I don't really know. And 2, when are we covering patching? Or a couple of words on brief basics of patching. So you're talking about you want an asset list and you want to update the asset list. So I don't know that we'll ever cover patching because I don't know that we have a lot of options in terms of doing patching, right? Like my understanding, and again, this is not something that I normally deal with, but my understanding is like Steam does the patching the way it does the patching, right? So like when we put our game up there or whatever we're going to do in terms of releasing the game, we don't get to do patching, right? So you know, I don't know that there's really anything we're going to do with patching because the patching is determined to a large extent by the distribution service. You know, if we put it on GOG Galaxy or something, like they have their own patching as far as I know. So I don't actually know to what extent we are allowed to do anything with patching. So we may never cover that. But in terms of how to deal with it, like, you know, it's a pretty straightforward problem. You know, you can go read about rsync. You can go read about standard, you know, diffing systems. And, you know, if you want to go those routes, you can go those routes. There isn't something special about game assets that makes it any different from other people's synchronization, really. So, what was the reason for dismissing the use of fibers early on? So the reason is because fibers don't give us what we actually wanted out of threading. Like, our problem right now is not that we need to interleave work on the same CPU core. Our problem is we need more work available for the processor, and fibers don't do that, right? So we don't actually have a use case for fibers at the moment. And I don't think we ever will. I don't anticipate us ever needing them. We want actual real threads. Have you made any progress on the license text for ports for other programming languages? Unfortunately not. I tried multiple times to do this. Unfortunately, the liability is a little bit difficult. So like what I was trying to figure out is how I would get it so that Molly Rocket isn't liable if someone like basically ships a virus as part of their port to some other language and we include that with our zip file. I don't know what happens there, right? And I haven't been able to find anything definitive that says how we deal with that. So I've been considering other options for how to do the licensing, which is basically saying maybe something like you have to stay 100 days behind the mainstream, but other than that, you're allowed to post it or something. I was trying to figure out things where we could basically just allow people to post it and just have some restriction on there so that we still get some of the exclusivity out of it in just short term. I don't know. It's a very tough problem because lawyers. Would it be possible for you to boost the sound of your voice on stream? I've always found that it is barely high enough, even with all mixers at maximum volume possible. So I think you've got something weird going on because actually it's at the maximum volume, right? Like if you actually look at what's happening here, it is actually at the maximum volume. It doesn't really go any higher than that without just straight up clipping, if that makes sense. All right, I think that's it for today. So I'm going to go ahead and wrap things up. Close this down, exit. Make sure we've saved our Blackboard. All right. Thank you everyone for joining me for another episode of Handmade Hero. It's been a pleasure coding with you as always. It was a good Blackboard session today. We covered threading and we created our threads, but we haven't actually done anything with them. That will be tomorrow's job to actually start pointing our threads towards something useful. And in order to do that, we will have to start talking about synchronization, which is the next big topic in multi-threading. So we'll have to do quite a bit of Blackboard work this week because there's a whole bunch of topics that need to be introduced, but slowly but surely we will get to the point where we are running multi-threaded in the renderer, and that will be a good thing. So, thank you everyone for joining me. If you would like to follow along at home with the source code, you can do so by going to handmadehero.org and pre-ordering the game. It comes with all the source code, and you can download it every night after I'm done. You'll get a link that you can just keep using to download the source code anytime you want. We also have a forum site you can go to ask questions or to get coding resources like ports to Mac or Linux or annotated episode guide that the community maintains, stuff like that. It's really handy. We have a Patreon page where you can support the video series if you'd like, which is very appreciated. And we have a tweet bot that tweets the schedule at you. We also, thanks to some donations by folks who helped write the JavaScript, and in fact, I do not know how to pronounce either of their names, so I will simply point you at the thing that says their names. I'm going to say like Remy Rakic, let's see, and maybe Jakob Munk Anderson. I don't know how to pronounce these names. They are names whose pronunciations I probably butchered. But thanks to them, we also have the live button now actually does a reasonable job at telling you when it's actually going to be live. So you can also just check this guy and he'll do it. But the tweet bot tells you the schedule in advance. So if you want to know kind of what the schedules will be for the week and to get a reminder in the morning or stuff like that, that's the place to go for that. It's pretty handy. So thanks everyone. I hope to see you back here tomorrow. Tomorrow will be regularly scheduled time slot, 5 p.m. Pacific Daylight Time. Hope to see you all here for that. We will go over how to get those threads actually doing some work for us, which I think will be good. So hope to see you there for that. Until then, have fun coding, and I will see you next time. I'm going to stay on the stream just for a few seconds because apparently there's some story I'm supposed to check out, so we'll take a look at that. Okay, thanks everyone.